Simpson's one-third rule. Simpson's one-third rule is an extension of trapezoidal rule where the integrand is approximated by a second-order polynomial. Here we can see a function and area under the curve of that function. To approximate that area under the curve, we use integration for the first-order polynomial in trapezoidal rule and second-order polynomial in the Simpson's one-third rule. For second-order polynomial, the equation will be like this with three unknowns a0, a1, and a2. To make three equations for three unknown, we will have to suppose three points on this graph, which will give us the x and y values for the equations. We will choose the first value a, the second value b, and a third intermediate value between a and b and their corresponding y values, like this. By substituting these values into the first equation here, we will get something like this with three equations and three unknowns. Here we have three equations and a0, a1, and a2 to be the three unknowns. By making the unknowns the subject of the equation, we will get something like this. Now we can solve this equation and get our unknowns, find our unknowns here. Now integrating the first equation, we will get this equation here, and substituting all these values into this equation, we get something like this. This equation is a raw form of a Simpson's one-third rule. Since for Simpson's one-third rule, the interval a to b is broken into two segments. The segment width is h is equal to b minus a divided by 2. Substituting this into the raw form we get here, we can get the final form of Simpson's one-third formula, which looks like this. Notice that there is an h by 3 here, which is in essence 1 by 3, so which gives us the name of Simpson's formula. To clarify further, we'll do an example, which is a rather short one, because Simpson's one-third rule is a plug and play type of formula, so it's very short to do the example. Here we're given a data set and are told to integrate it using Simpson's one-third rule. We'll have to make sure first of all that this can be done by Simpson's one-third rule. For that, we'll have to make sure that there are 4 or even number of intervals, or in other words, odd number of data points. Here we can see that we have even number of intervals. In this case, we have 4 intervals: 0 to 1, 1 to 2, 2 to 3, and 3 to 4. Or in other words, we have 5 data points or 5 values of I or x. You can also see that the xi value have a constant increment in them, that is of 0.1, which will be the h in the formula of Simpson's one-third rule. Here is the formula for Simpson's one-third rule. We can see that these are the first and last values, y0 and yn, in this case y4. These are the odd values in between of the first and last values, that in our case we'll have first and third value, and these are the even values except the last one. In between the first and last one values, that will be the second value in this case. H is defined as the increment in x values, so we have 0.1 increment here. Substituting these values here, we have y0, we have yn here 2.151. These are the odd values multiplied by 4. This is y1 and this is y3, and this is the second value here at x is equal to 1.2. Solving this, we can get the answer to this, that is area under the curve of this function graph here, to be 0.7292, correct to 4 decimal places. That's all for Simpson's one-third rule. Thank you very much.